Let's get started. I just want to make sure this is working. Okay, so there was a technical difficulty operator error last class in that only 4 seconds of the lecture recorded. So we don't have that. So if you were hoping for that, you missed Monday, you were sick, or still on weekend mode, I apologize. It wasn't planned. So if you go, when you're studying, if you go to look for lecture 22, it won't be on Canvas. And that's my fault. I don't know how that happened. Yeah. Homework 20 coming around. This was the unfortunate homework. If you were one of the people who got a 0, okay, you are more than welcome to sit down with me and go over it. It's not necessarily an issue of doing it the way the book does it. I'm not going to tell you how to do things. I think the only right way is how to get the right answer. It was just very obvious in terms of like the same variable names that they use, the same step by step. It was pretty obvious from my point of view. But if you didn't, you are more than welcome to come sit down with me and not plead your case, but go over it. All right. Any other questions? All right. So last class we developed how to analyze and calculate the internal forces, and we started with beams. Okay. We had a hint of that with trusses because they were 2 force numbers, and we just looked at that tension or compressive load. All right. So we've seen that before, but we added another layer with our shear force and our bending moment internally in the beam, all right? And recall that in order to analyze these correctly, okay, we cut the beam at the location of interest, right? Your homework 21 was at a discrete point, cut it, and you applied your equations of equilibrium, all right? But in order to apply your equations of equilibrium in an accurate way, you needed to apply a correct sign convention, right? A sign convention similar to how we analyze trusses. Okay, we applied a sign convention, so our numbers at the end of our math mean something. All right? And if you remember, our axial force, that force that's along the line of action of a member, tension is positive. Right? This is nothing new. Nothing new with how we solved with our trusses. Right? That's review. Our shear force, a positive shear force, is trying to push the right-hand side down. Right? That's the simplest way we can say it. It gets a little tricky, as you might have figured out, if you're tilted, okay? But that doesn't affect it. That doesn't affect your sign convention of your shear force. It's still the right-hand side, or the left-hand side or the right-hand side, pushing up or pushing down, right? That positive sign convention. In a bending moment, that positive bending moment is concave up, trying to bend that beam concave up. And remember, this is irregardless of the right-hand rule. Okay, so don't mix these two up on homeworks or on a test or on a lab. Okay, this is independent of the right-hand rule. All right? So if you remember this example from last class, all right, we have this beam just with a vertical force F loaded at 3/4 L. All right? And to solve for the internal force, okay, we cut the beam. Solve for the internal force at C. We cut the beam. We had previously solved for our reaction forces at A to be 1/4 F. Okay, that AY force to be 1/4 F. There was no lateral force in AX, even though it's a pin constraint. AX ended up being equal to 0. And we applied our internal forces, okay, with a positive sign convention. Alright, and we found that our shear force was equivalent to 1/4 F, the same as our reaction force, and our moment to be FL over 16. Okay? And so this was at a very discrete point, at point C, where we applied our equations of equilibrium after we've demonstrated our internal forces with the correct sign convention. Alright? But what if we wanted to solve for these internal forces at a point other than C? Okay. With the method that we learned on Monday, we would have to move our cut. All right? We'd have to move our cut. So for example purposes, I ask for the internal forces in the middle of the beam. All right? So our internal forces at L over 2. So using the method that we've done, okay, that you just submitted a homework on, our reaction force stays the same. That's independent of where we cut. We keep our same sign convention. Okay, our axial force is 0. We keep our same sign convention for our shear and our moment. And then we apply our equations of equilibrium. Right, this is what we've learned up to this point. So if we sum the forces in the y, okay, we get our shear force to be 1/4 F. It's independent, right? It's not changing at C or in the middle of the beam. And it shouldn't, qualitatively, because there's no loads. There's no loads that would change that shear in between these 2 points. Okay? But if I sum the moments, okay, if I sum the moments at A, okay, is this going to change? Why, Nicole? Because our moment arm is different. We're at a different point in the beam. That's exactly right. So if I sum the moments at A, okay, I have negative, okay, if I'm looking at my shear force, negative, it's applying a clockwise rotation, 1/2 L, there's my moment arm, times 1/4 F, which we've just solved for, is our shear force, plus my bending moment. Okay. As it's drawn, it's a counterclockwise orientation, so this is positive by the right-hand rule. Okay. 2 different things. So if I solve for my bending moment, I get 1/8 F times F. Okay? And so this should make sense. If you think about an extremely long beam, okay, that's only loaded, I was going to bring a yardstick, but I forgot. It's only fixed on its ends. The further you are, the closer you are to the center, right, if you apply a load, the easier it is for that beam to bend. Right? But think about if you're holding a yardstick and the closer you get to the fixed connection, it's hard for it to bend, right? So at the middle of the beam, your bending moment is greater than where you are fixed. Right? Does that make sense conceptually about what's actually going on in the beam? You've seen it before. You may not have analyzed the internal forces, but everyone knows it's harder to bend a beam, or it's easier to bend a beam in the middle. All right? So this is nice, right? This is an easy method. It's straightforward. We're good at our sign convention. I know you guys are rock solid on your equilibrium equations. But if we wanted to see how these internal forces change throughout the beam, okay, that would be extremely tedious to make a cut at every single point, especially if we wanted to get a continuous representation. Okay? So we have a method to do that allows us to continuously solve for these internal forces, okay, across the beam. We do that through shear and bending moment diagrams. All right? And so that's what we will learn today. All right? And so it's one step further. Okay, it's one step further from what we learned on Monday. Okay? The only difference here is that we are going to be discretizing the beam between loading conditions and analyzing. All right? So your first step, okay, this is the first step since week 3. You guys have it down. You solve the reaction forces. All right? Your next step, okay, this is the difference. This is when you discretize the beam based on applied loading conditions. When I say applied loading conditions, I mean applied forces and applied moments. Those can be distributed loads, those can be point forces, those can be moments, right? That's pretty much what we cover in this class. Right? And then you make a cut and you solve for those internal forces within that section. Right? And then we graphically represent our results. So that fourth step, okay, we will kind of solve as we work through an example. Okay? So if we work through this problem, okay, a beam with two loading positions. Okay, we have a point force of 80 pounds at point C, an applied moment at point D. Right? So your first step, okay, get out your calculators. Your first step is to solve for your external reactions. Okay, so if I draw my applied loads, okay, what are my constraints? What are the reaction forces? What do you think, Patrick? The reaction forces. An upward force at B. Okay, we're sitting on a roller. It's preventing translation only in the y direction. It's free to move horizontally at B. Good. And the constraint force at A in both the x and y directions. Remember that the orientation of these constraint forces has no sign convention. Okay? Doesn't matter. Doesn't mean anything. Your math will tell you if it's drawn incorrectly. Okay? So to solve for the constraint forces, okay, how would you solve for the constraint forces right away? Sum the moments at A, Drew says. Okay. So give me what's in that equation, Nick. You sum the moments at A. Times 2 is by times 8. And 200. Right? So we're sign conventions here. We're in the right-hand rule. Okay, that still applies. Okay, so we've drawn a clockwise moment here. Okay, so our applied moment of 200 foot-pounds is negative. And our By, or our 80-pound force here, okay, is applying a clockwise rotation about A, so that is also negative. Okay. So solving for By, immediately, we get By is equivalent to 45 pounds. Right? So now that you've summed the moments at A, we solve for By, then you can easily sum the forces in the Y. To solve for AY, so AY minus 80 plus BY plus 45 equals 0. So we solve for AY to be 35 pounds. Okay. So we've solved for our reaction forces. Okay, if we sum the forces in the x, we know that AX is equivalent to 0. Right. So in looking at our steps, we've completed step 1. Okay. And now the second step says to section off the beam based on your loading conditions. All right? So to do that, we section off the beam. Roll this up, see where we're at. We have our beam. Let's apply our loading conditions. So we know we have AY of 45 pounds. We have an 80-pound applied load at C. We have a 200 foot-pound moment at D. And we have a BY it's 30 pounds. our loading conditions. We've blown it up. Okay? And so we need to discretize our sections based on our loading conditions. Okay? So we have 3 sections here. We have between A and C, between C and D, and between D and B. Okay? So to discretize, I'm just going to draw lines. Section off. Section off between these points, right? And so now our third step is to solve for these internal reactions in these sections. Okay, and so our methods now are the same. We make a cut in these sections, all right? And so this first section, between A and C, I'll call section 1. Okay. So x is between 0 and right before x equals 2. So we're making a cut right before x is at C. We're making this x, and you're analyzing from point A. So if I make my cut right before C, right when x is 2, and draw your free body diagram, the same way you learned on Monday, the same way you just did your homework on, you apply your external forces, your external reactions in this case, at A, and now we draw our internal forces at this cut with the positive sign convention. So we know our shear is pointing down, it's trying to push the right-hand side down. Our bending moment is in a counterclockwise position, it's trying to go concave up, and our axial force is in tension. And we know that's going to be 0. We really, in the next 2 lectures, and in your 5th lab, we're only going to focus on shear and bending. That's the interesting stuff. Your axial force is only going to change, okay, if you have some loading conditions that are applied laterally. And those will remain constant throughout the beam. Unless you somehow, there's some sort of internal gear or something that's applying loading conditions within the beam. So to solve for my internal forces, in this first section, I sum the forces in the y. We know that my shear is 35 pounds. From A to C, that internal shear force is 35 pounds. If I solve for that moment, if I solve for my bending moment, you can sum the moment at A or at your cut, right? We have 2 points here, at A or at your cut, doesn't matter. Okay. For this example, I sum them at the cut. Okay. So this distance across the beam is x. Okay. Because as Nicole said earlier, your moment is changing as your moment changes. Your internal bending moment is a function of where you are at x. Okay, so we need to describe a variable that represents that change. Okay, so to sum the moments at the cut, I get negative 35x. Right. This negative is negative because it's applying a clockwise rotation, and it is an x distance away from the cut. I'm not at 2, because I cut it directly right before it, and we need to describe how that moment changes as a function of x. So 35x plus your moment, okay, so you can solve for your bending moment to be 35x. Okay. So in this method, yeah, Keenan?
Why can't you do why can't you multiply 2?
Because we're not at 2. We're not at x equals 2. Okay? The moment, the internal bending moment at x equals 2 is going to be 70 foot-pounds, right?
Yeah. What if you say the units
It doesn't matter. Okay. So at x equals 2, so this is a good question. Keenan asked, why can't you just say 2? Because that's a discrete point. Okay. That's what your method was on Monday. That would be, what are the internal forces at C, and we would have to use x equals 2. But we want to solve continuously what that bending moment is as x changes. Okay. That leads me into my point, so we can show that graphically. Okay. So on this method, okay, this last step, it says graph results. Okay. I like to do these kind of together so I can see how it's changing and to see if I've missed anything. I'll make sure we understand that. So to show these graphically, okay, we have our shear force and our bending force, our bending moment, excuse me. Okay. Just graphics, x and y graphs. Okay. So from x equals 0 to 2, in this first section, my shear force is 35 pounds. Nothing's changing. Nothing's changing between A and C on my shear. But my moment is changing as a function of x, and that's why I have a first order polynomial. So as x changes from A to C, does my moment increase or decrease in magnitude? Increase. And we can see that both conceptually, right? As we know, we move further away from a fixed connection, our moment increases. But we can also look here in our equation for our moment. A first order is a positive slope of 35. So when x equals 0, our bending moment is 0, right? And that immediately needs to be the case. At any fixed connection, you can't bend, right? There's no bending internal moment, right? But as x progresses, okay, our bending moment increases until we are at x equals 2, and we know it's 70 foot-pounds. So Keenan, if you had plugged in and said, if we use x equals 2, you would only find this value. But here, we can look on our graph and immediately pull out what our bending moment is between x equals 0 and 2. All right. So we have a second section between C and D. Okay. So we're making our cut, and now right before D, but we still need to include, we still need to solve from A. Okay, we can't make two cuts here. So if you draw your free body diagram, from A, and AY is 35 pounds. We now have our 80-pound external force applied between A and D. So 80-pound force is there, and we apply our internal forces with our positive sign convention. So shear, right hand side down, bending moment, concave up. Yes, Evan? So Stefan asks, now that we know that our axial force is 0, do we even have to write it? No, I don't. If you want to show it, it doesn't hurt. Okay. But no, that's not all. That's most often the case in these beam problems. Okay, but as soon in these horizontal beam problems, but as soon as we get a bent member or a lateral load, that's no longer the case. Okay. So if I've made my cut right before D, okay, and x is now including 2 So right before 4. Okay. So our distance between A and C we know is 2 feet. And our x, so we're now going all the way up to our cut. But we're starting here at A because we can't make 2 cuts. So this first section, this is where we're making our cut, this is where we're analyzing it, but our x is in reference to A. Does that make sense? So then we can apply our equations of equilibrium. Okay? You guys should have down. So your shear force is what? What's your shear force, Chenley? You don't know? Can anyone help Chenley out? Yes, Sarah? 35, okay, minus 80, minus your shear, is 0. And solving for the shear, you get negative 45 pounds. That makes sense, Shenlang? It's just your equation of equilibrium, just some of the forces in the y. Right. So then to solve for the bending moment, sum the moments about the cut. Your moment, your bending moment, is again a function of x. So we have negative 35x. But how would I represent this 80 pound? Because it's no longer, it's not 2 feet away. It's 2 feet away from D. But how do I represent how that 80 pound axial applied force is affecting the bending moment between C and D? Good, Keegan. 80 times x minus 2, right? That's describing how this distance is changing. Okay? So we have plus 80 times x minus 2 plus your bending moment. Right? So solving for your bending moment, negative 45x. Sorry, guys, I'm starting to act like your physics teacher. Don't tell me. Negative 45x plus 160. Okay, that's low. I'm going to write it up here. The moment is negative 45x plus 160. Okay, so from A all the way up until this cut, our bending moment is again a function of x. So then we go over to our shear and bending moment diagrams, okay, and represent your results graphically. So our shear force in the second section is negative 45 pounds. So we're at negative 45 pounds here. Okay. What's 35 minus 80? Not negative 65. You're sitting in the front row. Negative 45. This applied load, okay, causes an instantaneous change in your shear force. Okay. We found that using this method, okay, as we've sectioned off. Okay, but you also see this in your results, in your graph. So this is a sanity check. If we had gotten negative 65, but we only were applying an 80-pound force, check your math. Okay, so there's some sanity checks here for you to use. Yeah, no? How do you know where to draw the lines, like to scale? You don't. Just label it. Yeah, you could put your moment up here. This is how I was taught it. This is, I think, how the book does it. It's just how it. These are two separate graphs that we're sharing. We're sharing the discretized points in our load equations. So our bending moment, negative 45x plus 160. So your bending moment when x equals 2 is 70. Right? And it sure as heck better be 70 because this applied point load is not going to immediately change your moment. We will see what happens. We will see what causes that. But your moment when x equals 4, plugging in 4 for x is negative 20. Good so far? Good job? It is significant that we're kind of bigger than the and you see that causes a symmetric deformation. But x is not it's an arbitrary variable. We could choose y or p or q or whatever. But it's describing how our internal forces are changing across the length. Yeah, let's see. For the 35, it's not 2 plus x. Because it's with your equivalent force couple systems. And this resultant force is independent of where it acts, right? Just in your forces. The resultant force, the distance doesn't matter. Does that make sense? Alright. So our third section, okay, I'm going to come over here now. Okay, this third section between D and D. So we're analyzing the internal forces between x's 4 and okay. So our method stays the same. And we make our cut between C and D. We draw our external forces. We have a 35-pound reaction today. An applied force of 80 pounds. We now have an applied moment. An applied moment at D in a clockwise direction. And we also have our internal forces. Our shear and our bending moment. And I'm going to be lazy. Stefan said it was okay. We know that our axial force is 0. So again, you apply your equations of equilibrium here. Sum of the forces in the y. 35 minus 80 minus my shear equals 0. So my shear is again equal to negative 45 pounds. And it should be. Because there are no forces, there are no applied forces that would cause a change in shear. Okay. But what's going to change? Your moment, right? That's the more interesting part. So our shear force is again negative 45 pounds. But our moment is going to be different for 2 reasons. Okay, for 2 reasons. What are those? Our moment is different between D and B as it is in comparison to between C and D. Why? Good job? Our moment arc is changing, right? The further away we get, or the closer we get to a reaction, our moment arc is changing. But we also have a loading condition here. Okay? We have an applied moment at D that we did not take into account in our second section, as we cut right before. This applied moment, Moments are free vectors, and they act independent. That's why there is no distance attached in our moment. Okay, so in our moment equation, we have negative 200, the clockwise moment, negative 200 minus 35x. X is my length of the beam. And it's 2 feet between A and C. So minus 35x plus 80 times x minus 2, as Keenan said earlier. We're looking for this distance now. Even though our x is qualitatively larger than it was in our second section, we still represent it the same. X minus 2 plus our bending moment. So solving for my bending moment, negative 45x plus 360. Okay? So, at x equals 4, your bending moment is 180 foot-pounds. So at x equals 4, we jump up to 180. What's negative 20 plus 200? 180. This applied moment causes an instantaneous change in your bending moment. Right? I mean, it should. If you apply a torque at a point, it's going to change the torque at that point. Right? We jump up to 180, and because this is a linear function, x equals 8, your bending moment is 0. And it, again, should be 0 at a connection. Okay? So we've drawn your shear force and your bending moment continuously throughout the beam. Okay? So let's take a moment and interpret these results. Okay? And recap what we learned. These applied forces, okay, these external forces at A, at B, and your applied force at 80, okay, cause an instantaneous change in your shear. Okay, an instantaneous change in your shear. So you're drawing these and you see these externally applied forces, okay, make sure your methods are matching up with what you know. These cause an instantaneous change in your shear. Okay. Similarly for your moment, an applied moment causes an instantaneous change in your internal bending moment. All right. And also check that at connections, at fixed or pin connections, your moment is 0. Okay. So let's think about a couple design decisions that we can do for this, right? Because that's what the whole goal of this is. As an engineer, let's say you are some sort of structural engineer, and this beam is actually 800 feet long, and we've just scaled it down. An 800-foot beam, you're not going to transport it, right? So you've seen those carriers, they break up those I-beams. Where do you make your cut? And looking at this, where do we make a cut? Closest? Close to each point where the forces are applied? Not necessarily. Yeah, Curtis? Where what is closest to 0? Exactly. You would do it where your moment is 0. Because if you make a cut, you're going to have to connect it with some sort of gusset or pin connection, right? It's not going to be a continuous beam. There's going to be different materials. Things are going to change. Okay. But at the point, okay, where there's 0 bending moment, okay, is an excellent place to cut the beam so your connections don't have a large amount of torque applied to them. Okay? And also, you're engineering a bridge, right? This is actually a bridge deck. What are your hot spots? What do you care about? We've made the cut, we've moved it to the construction site, and now we want to make sure nobody dies. Where would somebody die? Where would it fail? Same place? In the moment zero? There, Keenan?
Zero one is the highest highest shear force.
Half right.
I mean like their highest change in shear force.
Not change,
So
not
like
magnitude.
Let's see.
Right. Yeah, looking at our magnitude, our largest shear force is 4 to 5. Even though there's an abrupt change, we're already loaded over here. So section 1 is absorbing some sort of a load. But we're at 45. Our magnitude of our shear is at 45 pounds from C to D. But what causes things to break also? High moment, right? This torque. This maximum torque coincidentally coincides with your maximum shear. So your chances of failure, this is getting into reliability, your chances of failure are largest where your maximum torque and your maximum shear force are. Okay? So just a couple applicable points. Right? But this stuff isn't just math, right? You go into any structural analysis and use this stuff. Right? You can use these to understand what's actually going on in the beam. Okay, so back to Jack's point, is it ironic that it's symmetrically loaded? Okay. It is, because we can represent how the beam's going to deflect. Okay. So how the beam's going to deflect, if we look at our bending moment, a positive bending moment does what to the beam? Go back to your sign convention of your internal forces. What's that? Concave up. So a positive bending moment. Okay. So we are from A to between C and D, we're bent concave up. Okay. Then we have a slight bit of a negative bending moment, okay, in which the deflection of your beam is actually concave down. Okay. And then we're positive again. So we're bent concave up. Okay. This is very much exaggerated. Okay. But we can see the deflection. Right? And see that as that inflection changes, that's the failure point. Alright? Any questions on that? Okay, so let's step it up. Let's step it up a level. Confirming a distributed load. So your distributed load, right? We have a beam, a cantilever beam, that is a free end. There's a free end at B, and we're fixed at A. We're fixed at A. So what are our connections? What are our external constraints? 40-pound applied load. We have some distributed load of 20 pounds per foot. Okay, but we're fixed today. What are my constraints? We have a force inside of a y, and we have a constraint moment, then it fixed connections prevent translation and rotation. There's also an x, right? It's fixed, but we know your constraint at A in the x direction is 0 because there's no lateral forces. Okay. So, if we sum the forces in the y, we can jump ahead and do that immediately. Sum the forces in the y, we can solve for ay. So we have ay minus 40. Think back to module 3 with our distributed loads. How do I represent this as a single force? Length times width. Take the area under the curve. Okay? We can do that by integration. We learned that method. But we can also just take the area under the curve because we're given the dimensions. Okay, so my height, 20 pounds, and it's at a width, 20 pounds per foot, and a width of 10 feet. Okay, so the magnitude of that resultant force under the distributed load is 200 pounds per foot. So solving for ay, we get 240 pounds.
That's supposed to be minus 20 times 10.
It's supposed to be minus 20 times 10. Yes, it is. Did I get my signs right there?
Your answer's still right.
Yeah, my answer's right. Thanks. Okay, so then to solve for this constraint moment, okay, because it's a fixed connection at A, so the moments at A, we get minus MA minus 40 times 14. Okay, what about this distributed load? You're all the right words. So you said you just find the centroid of the distributed load. Okay. So your centroid, so our magnitude, 20 times 10, your centroid, it's a rectangle, so we know it acts at the midpoint of 5 feet, right? Did that blow anybody away, or are we okay with distributed loads? We use them. Solving for the moment at A, we get negative 1560 pound-foots. Okay. So it actually was drawn, we drew it clockwise, okay, it's actually acting in the counterclockwise direction. Alright? So our second step, okay, and we discretize the beam. Discretize the beam with our loading conditions. AY 240 with a moment 1560 foot-pounds. It's a distributed load. 20 pounds per feet with applied force of 40 pounds at the free end. So setting this up, and I'll only be able to set it up because we're running out of time. Our discrete loading, we can discretize it based on the loading conditions. Okay, so when you see a distributed load, include that distributed load. Don't section it off in the middle. So we only have 2 sections here. We have 2 sections here, so I'll set us up on this first one, okay, distributed load, because it's the most interesting. And then I'll post the final answer. So in section 1, the x is between 0 and 10 feet. So along this internal force, along this beam, we're finding the internal forces, right? And they're not constant, because our loading condition is not constant. We're continually applying a load. We draw our free body diagram. Okay. We apply our shear, apply our moment, apply our reaction forces. We have a distributed load here. Now we are coming from A, we're taking x with reference to A. Okay, so you apply your equations of equilibrium. Okay, I'll throw them up so you can work it and make sure you get the right answers. We get our shear is 240 minus 20x. And our moment is negative 10x squared plus 240x minus 1560. So this is a second order polynomial. Okay. Your bending moment and your shear force under a distributed load are both a function of x. Okay. So do we have any other questions on this method? Okay, I'll make sure to post the work example here. All right. Remember, you have pre-lab today at noon, in which we're actually going to be measuring this stuff. All right.